Hello dear students. So, we will continue our discussion to derive the radial growth of a droplet subject to the conditions that are existing in the ambience. So, we will take the diffusion to be the main process by which the droplet is growing in size. Right. So, we have stopped at this point where we have derived an expression for the density change with respect to the density of the ambience at saturation in terms of temperature changes, latent heat and the specific gas constant. Right. So, if you say that the diffusion is the main process, let us say associated with the condensation is the release of latent heat which rises the droplet's temperature above the ambient value. So, in the integration, while we were identifying the limits of integration, we have seen that the integration is to be carried out from a temperature T e to temperature T r, where T e is the temperature of ambience and T r is the temperature of the at the radius or the surface of the droplet. Right. So, why is the temperature different between these two places? What is the physical process that is happening? Is in order to understand this, when the condensation happens, release of latent heat is of course is there. When the condensation happens, latent heat is released and this heat is attributed to the droplet, which rises the temperature from let us say T e to Tr above the ambient value. So, the diffusion of the heat away from the droplet. So, once there is a temperature gradient, once you say that the temperature of the droplet or the surface of the droplet is larger, there is obviously a reason for this temperature to go away or for the energy to conduct. So, how does the energy the gradient in the temperature compensate itself? By conduction. I mean the heat is given out. So, the diffusion of heat away from this droplet is given by this. So, this is a simple conduction equation where the rate of change of temperature, of course, the rate at which heat is given out with respect to time is of course something to do with the radius or the size of the droplet, the coefficient of thermal conductivity and the difference of the temperature. So, T r is the temperature of the or the surface of the droplet, capital T is the temperature of the ambience. So, if this difference is 0, then there is no heat conducted, of course, absolutely. But since there is a difference, why does the difference come in first place? Because it has to accommodate the latent heat that is released when the condensation happens, right. So, this is a simple conduction equation where the T is the ambient temperature, T r is the temperature at the surface of the droplet, capital K is the coefficient of thermal conductivity, right. So, the condensation of water vapor gives out a heat ml, right. ml is the amount of heat and the rate of release is L dm by dt. The rate at which this is released, L is obviously not a function of time. So, we keep it out of the differential. So, and we say that L dm by dt is the rate of change of rate of release of the heat. So, the latent heat of condensation is transported by diffusion away from the droplet. Assuming that there are no changes in temperature with steady state, we can simply derive these two equations. So, this is of course the rate of heat that is being conducted or being released from the droplet is of course L dm by dt. So, if you substitute this, we can simply say that the density of the vapor minus the density of vapor at the radius by T r minus T is the coefficient of thermal conductivity, this is the coefficient of diffusion and this is the latent heat. So, in our terminology, we can write this as rho V e minus rho V r divided by T r minus T e is K by L T. So, this is one equation we are going to supplement with our earlier equation. So, this is let us say this is equation number 1 from here. So, we call this as equation 2. So, how many equations do we have now? So, we have so for example, rho v minus rho v r divided by T r minus T e is equals to K by L D. Again, simply with the ideal gas equation, rho V r is E prime R, now we are talking about a droplet, right, by RV TR. What is this? The density, this is very important. This, of course, this is just an ideal gas equation. This is the density of vapor at the surface of the droplet. This is the curved at the curvature term involved here. This is the specific gas constant, and T, of course, is the temperature at the surface of droplet, right. Now, so here now we can involve, so if this is with respect to the curvature, we have to use the Kohler's relation or the curvature and the solute effect. So, we can write this expression as Es of infinite to 1 plus A by R minus B by R cube divided by RV TR, right. So, this is, let us say this is equation 2 now, and this is equation, by the way, this is rho VR, this is equation 3, right. So, we have equation number 1, which is this equation 1, we have 2, we have 3, right. Now, from these 3 equations, we will do some rearrangement of these 3 equations, and we will try to see how we can derive an expression, right. So, we can say that TR minus TE is L by 4 pi KR into dm by dt, latent heat, and the where m is the mass of the droplet. So, we can now combine these 3 equations as rho Vs minus rho Vrs divided by rho Vrs is equals to Ld by Kt to rho Vr minus rho V times L by RVT minus 1, right, or rho Rs minus rho Es divided by rho Es is equals to L by RVTR minus 1 times L by 4 pi KR TE dm by dt. So, this is TR minus TE that we have used in this expression, right. So, TE still remains the same, right. So, T is still here, right. So, let us say this we will now try to simplify this equation, okay. Now, we know that rho E minus rho R is 4 pi d inverse into dm by dt. Dividing this expression with rho Es, and we will get rho E minus rho S divided by rho Es is equals to dm over dt into 1 by 4 pi rho Es capital D. Let us say we call this equation as, in this order, what we call this equation as 4, and we call this equation as 5. Okay. So, this is 4 and this is 5. Now, let us adding equation number 4 equation number 5. We will get on the left hand side rho E minus rho R divided by rho ES plus rho RS minus rho ES divided by rho ES, which is equivalent to rho E minus rho R plus rho RS minus rho ES divided by rho ES. So, let us say rho R is equals to rho RS. That means the density at the surface is equal to the density at saturation. Okay. So, in this case, this expression reduces to simply rho E minus rho ES divided by rho ES. That is also equal to rho E divided by rho ES minus 1. So, the vapor density of the ambience with respect to the density of saturation can be defined to be equal to S minus 1. So, this term is equal to S. What is S? S is the saturation ratio, and yes, the maximum value that the saturation ratio is expected to possess is ideally equal to 1, right. So, the quantity S minus 1 is of course indicates the supersaturation. So, you have already, so S is the saturation ratio, which is 1 ratio. If it is ratio, it is 1, or if it is saturation, it is 100%. Now, this term itself can be maximum 100, and you take 100 out of it, I mean 1 out of it, then you will realize what is this supersaturation ratio, right. So, now this was the addition of LHS. This was the addition of LHS alone, right. Now, let us add the RHS as well. Adding the RHS of equation number 4 and equation number 5. We will realize 1 by 4 pi rho ES capital D times dm over dt plus L by RV TR minus 1 times L by 4 pi R K dm by dt. Now, it is of course equal to S minus 1. We have already done this, right. So, take dm over dt outside, then we will realize L by RVTR minus 1 to L by 4 pi RK TE plus 1 by 4 pi RT rho ES is equals to S minus 1, right, or dm by dt is equals to 4 pi R into S minus 1 divided by L by RV TR minus 1 into L by K TE plus 1 by D rho ES, right. So, what is M anyway, right? Let us say this is an important equation. So, what is M? M is the mass of droplet, right. So, M can be written as 4 by 3 pi R cube times the density of the liquid. mass is density times volume. So, this is the volume of the droplet, mass of the droplet, and the density, which is of course the density of the liquid, right. So, if you write similarly dm over dt, the rate of change of mass with respect to temperature. So, what should it depend on is the density, of course, which remains a constant, and of course 4 pi r square into dr over dt. So, the rate of change of mass will only depend on the rate of change of the radius. The remaining, of course, are constants. So, we will have to substitute this, of course. I mean, the point of making this, taking this derivative is to be able to substitute this into this, right. Right. So, let us say we know that from the ideal gas equation, rho ES, ES divided by RV T. What is rho ES? Rho E is the density of water vapor at saturation, where in ambience is equal to the vapor pressure at saturation divided by RV T, just the ideal gas law, right. So, let us say we use this density change R, where is it, R square dr over dt into rho L times 4 pi, 4 pi is equals to 4 pi r times the supersaturation ratio divided by L by RV dr minus 1 into L by K dE plus 1 by d rho ES. If you cancel this, you will simply be able to write R dr by dt is S minus 1 to L by RVTR minus 1 to L rho L divided by K T plus rho L RV dr over dt, or we can write it as R dr by dt is equals to S minus 1 divided by L by RVTR minus 1 L rho L divided by K T. This is just simple algebra. I am just trying to rearrange the terms for the sake of convenience, right. So, it should not be any worry if you do not understand. You just have to look at the previous slides, get all the equations together and rearrange them, or substitute according to the method that we have followed, you will be able to get it, right. So, this we are going to call as, so for in simple terms we are going to call it as dr by dt is S minus 1 divided by Fk plus Ft. So, what is this Fk? So, I am going to, so this is just a notation. So, this entire term is Fk and this term is Ft, right. So, what is Fk? Why are we calling it as Fk? Right. So, Fk is the thermodynamic term associated with heat, of course, and Fd is the vapor diffusion term. So, this term is associated with the diffusion and this term is associated with the thermal term, right. Now, at this point again we can introduce the solute and the curvature effects as R dr by dt is equals to S minus 1 minus A by R plus B by R cube divided by Fk plus Ft, right. So, this is the generalized expression for the growth of a droplet. How does it change with respect to time? So, we have all the constants, all the variables that will tell you what is the concentration of liquid, what is the concentration of ambience, what is the density because of the ambient vapor, what is the gas constant, what is the temperature, everything, every parameter is given here, which will characterize or which will tell you the characteristics of the vapor and the droplet. Now, given this, so we can find how the radius of a droplet changes over time. That's the basic idea, right? Let's say, so if this is the case, then when, let's say, when the radius r becomes sufficiently large, okay, then we can simply say that A by R and B by R cube will be negligible. Of course, they will just be negligible, right. So, in that case, we can reduce this expression as R of t. I mean, we are going to integrate this, and we, as R, a function of t will simply be R naught square, the initial radius, plus 2c t, where the constant c is s minus 1 divided by Fk plus Ft. So, this is the expression which tells you how the radius of the droplet changes with respect to time. Okay. So, what we have seen is, just to recap, if you see the mathematical treatment so far, for us to understand or appreciate the expression, what we have done is we have simply taken the Clausius-Clapeyron equation with the vapor and the liquid variables, right. Then we have rearranged it in terms of density, getting rid of the alpha, right, where we saw that first time how the vapor pressure at saturation changes with respect to temperature will depend on the density at saturation and the temperature and of course, the latent heat, right. Then we wrote the vapor pressure at saturation in terms of the ideal gas law, and we took a derivative and we equated the first two terms, and then we got this equation, right. After this, we take an integration of this resulting equation from the ambient temperature to the temperature of the at the droplet. So then we got this expression, right. Then we made a simple approximation when z is very small values of z, ln z 1 plus z is eventually equal to z, not 1 plus or not something. It is just z. So, we applied this approximation on this parameter, this ratio. Then we derived how the density changes between the saturation, between the radius, between the surface and the ambience in comparison to the ambience, right. So, then we got this expression, right. Then we introduced the variables of thermal conductivity and the coefficient of diffusion, saying that the diffusion is happening at the droplet surface, and this diffusion, the rate at which the diffusion is happening, the rate at which the molecules are getting attached to the droplets must release some latent heat, and this heat must build up a gradient and thus allowing a heat conduction to happen from the surface of the droplet to the ambience. So, we took all these parameters and we later introduced the solute and the curvature effects into this, and then we thought the mass of the droplet to be m, and we tried to find out the rate at which the mass of this droplet will change with respect to time. So, that is where the time dependence actually came into the picture, right. So, we took the mass to be equivalent to density times volume, we took a derivative of the mass, and that is where actually the time dependence has come into the picture. Otherwise, there is no time dependence so far in the picture, right. So, eventually we algebraically simplified all these things, and then we realized the rate at which the radius of the droplet changes is equal to simply these two terms, S minus 1 is the supersaturation ratio divided by Fk plus Ft, where Fk is the thermodynamical term, Fd is the diffusion term, right. So, this concludes the discussion about the diffusional growth of a cloud droplet, how it changes, how its radius changes with respect to time, right. So, we will stop here. So, I suppose you can understand this. Okay.